this section specifically talks about percentages or proportions that come from the sample and how they relate to the population itself. But before we get into that, we're going to do a quick little summary of some of the things we've talked about. Now, this whole section is about the idea of p hat, or the statistical proportion that then talks about the p or parameter that we're talking about. But before we do that, we talked about other estimators that aren't proportions, and we want to talk about whether they're biased or unbiased. And so when we were looking at the average height versus the height range, we found out the average height from the sample distribution was exactly equal to the, or very close to equal to the population mean, whereas height range was not an unbiased estimator. It didn't work very well at all. When we looked at the tank problem, the mathematicians that had actually solved the problem, they had used a simple taking the highest number and multiplying by 8/7. They found it to be a fairly unbiased. It matched the population when they found out that. Whereas some of you did things like the standard deviation plus the maximum number was way off. It was unbiased. Remember, unbiased just means off the target. So these are some estimators that are used, and so we have to make sure that our estimations, or excuse me, our statistics are unbiased ones. This whole section 7.2 focuses on sample proportions, and the proportion or percent for the population is p. Proportion in statistics, by the way, means percent. It doesn't mean two equal fractions. And then this one is the percent for the sample. So this is called a p hat. This little schmoobie over here is called a p hat. And just so you know, when you do the Google form, I cannot put this symbol of p hat into the Google form. So it's literally written as the words. So it's kind of silly, but that's the way it rolls. So just, you know. So since this section focuses on proportions, I want to make sure that you understand why some of the calculations that we can use are allowable. A proportion in this case is a binomial setting. In this case we're looking for orange Reese's Pieces. So it's a success if it's orange. It's a not. So it meets this requirement. We're going to talk about what needs to occur when we're sampling for it to be still to be considered independent, even though there clearly is not replacement. We know the number of trials ahead of time, and we know the proportion of success in the population. For example, this particular sampling distribution right here has a known ahead of time sample size of 25 and the number of samples that we're going to be taking. So the number here is 400, and then we know the proportion ahead of time of 15% of them are orange. So when we're looking at a proportion, we can treat it like a binomial random variable. So when you were looking at the Reese's Pieces simulation, you were asked to come up with some information. How does the shape change, the center change, the spread change when we change the sample size or the initial parameter p, or the population size as well? So let's look at what. So the shape, sampling distribution of p, approximates a normal curve. It's even closer to a normal curve when you increase the sample size, right? It looks a little more like a normal curve when you increase the sample size. And also, because p hat is considered a unbiased estimator, the mean of the proportion p hat is going to be in the 25 and the 50. It's going to be right there at the value of the proportion for the population. That doesn't change whether the sample size is 25 or 50, but what does change is the standard deviation. The standard deviation with a larger sample size So this one's the, whoops, this one's the 25, and the standard deviation is 0.071. This one is the 50, and the standard deviation is smaller, which means that there's less variation. So the bigger sample size, less variation. We'll see if that works also when we have a different proportion. So in this case, the proportion of orange ones was 45. Sure enough, the one with a higher sample size is a little more normal. It approximates the normalness a little more when you have a higher n. And then also the standard deviation is going to be smaller with a larger n. So of course, even though this has changed the proportion, we still have a standard deviation of 0.103 for the sample size of 25 and a standard deviation of 0.068. So it's going to be less variable with a higher number in your sample size. The center, because p hat's considered an unbiased estimator, p hat is equal to p. So the mean of all of those is going to center out right there at p, and the mean of all of these is going to center right there at p, so p is 45. And so that's, once you recognize that p hat is going to equal p. So I've already stated in the previous slides that the standard deviation is going to get smaller. The variability is going to get smaller as you increase the sample size. This is supposed to say of p hat, but it didn't come through very well. By the way, obviously, you're going to calculate the proportion of success by taking the number of successes out of the total number of your sample size. That's how we calculate a percent. But it's important, since we are defining p hat as a binomial variable, we're going to use this to derive the formulas that allow us to easily calculate standard deviation. So this piece of information is more like, where does it come from? Then you need to memorize that, because you, of course, can calculate a proportion number of successes out of the total number of size sample. You've been doing that since you were in 6th grade. This slide covers what is on page 443, that basically gives you the derivations, where the formulas for the connection between the actual population and the p hat comes from. If you want to go ahead and follow along with that on that page, or reading this slide right on, you're not going to be tested on this stuff, and I'd rather spend the time on this video going through more crucial stuff. To summarize though, when you have information about p hat and its relation to p, you can go ahead and the mean of p hat is the same thing. The mean of the distribution of p hat, please excuse me, is the proportion from the population, and the standard deviation is the square root of p times 1 minus p divided by n. So you're actually using the population calculation to find the sampling distribution standard deviation. But it has to meet certain requirements, and we're going to talk about that more in the next slide. We'll also notice that sampling distributions of p hat approximate normal curve, so you can use normal calculations, but certain requirements have to be met called the normal condition. So I'm going to explain those a little more clearly on the next slides. We can treat p hat and make and the connections between the sample and the sample distributions and the population itself, we can treat it like a binomial random variable, which then approximates a normal curve, but only if certain requirements are met. So when a binomial requirement requires independence, but where normal sampling is done really without replacement, because you're not going to ask a person the question and put them back in the pool and possibly get them one more time. So for us to be able to accurately use binomial calculations, we have to meet this requirement called the 10% rule. So I'm going to give you an example that we're going to use for the next 3 slides or so. So let's say we take an SRS of 1,500 first-year college students, and asked how far away they go, far away from home they go to school, and that's 35% of those students said that they were within 50 miles from home. Can we use binomial calculations with this particular thing since we sampled without replacement? So you're going to go ahead and check something. This is the formula that it says. It says that the sample needs to be less than minus than 1/10 the population. It's actually easier for me to think about it. If you can multiply the sample by 10 and it's still going to be less than or equal to the population, then you're golden. Both are correct. I just like it the first way better. So if I take 10 times the sampled size, and if that's less than or equal to the population, we're golden. Well, in this case, there's 15000. That's 15,000. It's definitely going to be less than the population of first-year college students in the United States of America, so that requirement is met. Hopefully you notice in the Reese's Pieces example that a value of 10 was an important value for us to be able to see the distribution approximate normal. So that has been solidified into a rule called the normal condition. And so if you can calculate these things and you find them to be true, then you can go ahead and consider the sample distribution as normal and make inferences about the population, but only if this condition is satisfied. So let's look back at our situation with our 1,500 SRS and a proportion of 35% of the people who live 50 miles from home. If we calculated that, we're going to go ahead and get 525, which is greater than 10, so it meets this requirement. But it also has to meet the other one. So we're going to take 1,500, and we're going to multiply it by 65, and that is going to be even a bigger number of 975. So that's greater than or equal to 10. So this condition is met. Now we can go ahead and look at a question that is going to allow us to use normal calculations and our normal CDF and all that stuff. So here is our question. So the standard deviation can be calculated by taking the square root of the proportion, 35, and 1 minus p its complement, 0.65, divided by 1,500, which is your n, and that works out to be approximately 1%. And then the mean, of course, is going to be just the 0.35. We're going to ask a question about this that looks at it, and you're about ready to see a really great drawing of so I've taken the information. We have our proportion of 35, and the standard deviation of the p-hat is 0.0123, which I have approximated a little bit. I mean, these are accurate, but I rounded at each point so I didn't have to write it. So the question is, what is the probability that the sample result will be within 2% of the true value? So I'm going to go ahead and I want to go to 37 and I want to go to 33 exactly. Now these are not exact numbers right there, so we can't go with our 68, 95, 99.7 rule. We're going to actually use normal CDF. So we're going to go ahead and, yes, those of you that prefer to use the z-scores and the table do that as well, but you're going to just go ahead and use your normal CDF, giving the lower boundary and your upper boundary and your mean and your standard deviation. So you would go ahead and put normal CDF. Your lower boundary would be 33 because that's 2 away from the mean. Upper boundary would be 37 because that's 2 away from the mean. And then you'd give the mean of 35 and your standard deviation of 0.0123. And it would go ahead and give you the approximately 90% because it's a 0.8968, so it's 0.8968. So about approximately 90% of the sample result will be within 2% of the true value. Key issues here are making sure you understand that the sampling distribution tends to be approximately normal, and you can use binomial calculations, and the formula is only if you meets your 10% conditions, and you can use normal calculations only if it meets the normal condition.